Okay. And while we're at it, let me actually put another definition here. And that is the concept of a subcover. What do you think a subcover is? Take a wild guess. What is a subcover? Yes. Excellent. So it's a subcollection of G alpha that is still a cover. So good. So a subcover of G alpha is a subcollection. Notice that when I talk about a subcover, I'm always talking about with reference to some open cover. Okay? It's a subcollection, and here's how we denote a subcollection. If the subcover is G alpha, and alpha is from some index set, this could be possibly uncountable, the subcover would look something like G sub alpha, and I want to denote that I'm picking specific alpha. Okay? So I might do the following. I might look at specific alpha and label them. This is going to appear funny, but I might label them but with its own subscript, gamma. Okay? Usually later on, gamma will just be a finite set. Okay? But this is one way to write it. Is a subcollection that is still covers E. Okay, question. If I take a cover and I take the subcollection that's all the sets, is that a subcover? Yes, it's still a subcover because it still covers. I haven't removed any sets. In this picture, maybe E looks like, maybe E looks, let me throw another set in here. Would you agree that this set I just threw in is kind of extraneous? So all the green sets form a cover, but I don't need all of them. I could throw this one away. The rest would be a subcover. Happy? Okay. Okay, good. So two important concepts here. Let's look at some examples, specific examples. How about an example in the real numbers? Let's look at the set. How about 1/2? Include 1/2, but don't include 1. So it's the half open interval. And I claim the following as a cover. See if you agree. So I claim this has a particular cover, which I'm going to call V sub n, where Vn is a interval, an open interval, 1 over n to 1 over 1 minus n. Okay, so picture please. 1/2. 1. And what are the sets here? Well, I probably should start, so this isn't empty, I probably should start n at what? How about 3? Okay, so by subscripting it with an n, this is a collection that's indexed by the natural numbers, and I'm starting at 3, and this just means keep going. Okay. Okay, so what does this set look like? Or what does this cover look like? Each set looks like, the first set is 1/3 to 2/3, so it might look something like this. There's the first set. Yes? What's the second set? 1/4 to 2/4. 3/4. 1/5 to, I actually have to do math. 4/5. 1/6 to 5/6, etc. And you can keep going. You get ever increasing intervals. Yes? Are these open sets? Is this an open cover of the set that goes from 1/2 to 1, not including 1? Yes. Why? Well, we're not going to, we'll just say why. Is it clear that that 1/2 is covered? Yes, by all the sets. Is it clear that 3/4 is covered? Yes, not by V4, but by V5. Yes? And would you agree that any point just to the left of 1 eventually gets covered by one of the sets? Yes? Okay. Good. So this is a cover. But there are lots of covers for this set, right? It also has the following cover. How about the cover that just goes from 0 to 2? Just one set. So this cover has one set. Is this an open cover? It consists of one set like this. Okay. Yes? Happy? Yes. So the curly braces indicate a set. And the parentheses indicate the bounds of this interval. So this is the set containing one element. This is a set containing many elements where I've indexed them by a natural number. Okay? Excellent question. If I left this off, this would be a single set, but I'm talking about a collection. So just to be really precise, I'm saying this is a set containing one element. Okay? Yes? Ooh, excellent question. So the question is, do we ever need an uncountable index set? And the answer is yes for some metric spaces, although it turns out for most of the metric spaces that we care about, you could have a countable collection, but sub-collection, right? But for instance, here's a cover of the real numbers. Let's take all balls centered at any possible point. That's an uncountable collection of open sets. Okay. So yeah, in fact, let's do this example here. Oh, so it has another cover. Also, it has this cover. How about the cover? Let's call this W sub x, where W sub x is, and this is all x in 1/2 1. So this is kind of a cute trick. I have a cover here where for every point in this set, I have an open ball around that point. How about an open ball around x of radius 1/2? Would you agree this is a cover of the same set, and basically around every point I'm taking a ball of a particular radius? 1/2 is huge, actually, right? So this is much, the picture is bigger. But okay, to make this just a little more interesting, let's make this 1/10. How's that? Then that's more like this picture. Would you agree that this cover just consists of a bunch of balls around points? And how many of them are there? Uncountably many, one for every point between 1/2 and 1. Are you with me? These are all covers, yes? So one of the questions that you want to ask is, do we need everything in the cover? For these particular, I gave you 3 different covers of the same set. Do we need all these sets? Given a cover, so here's a big question. Given a cover, do we need all these sets to still cover the set? Okay. So let's look at these 3 covers. The V's. Do we need all the sets to still cover this set?